Hi, it's Robin. Today we'll be looking at 10 seldom used Commodore 64 BASIC commands and features. Some of them didn't get used much because we just didn't understand them, or we couldn't think of a use for them, or maybe because they're just not all that useful. As always, there will be an index in the description below in case you want to jump around. Before we get to that, I should mention that I have a second channel now, cleverly named 8-Bit Show and Tell 2, which will have other 8-bit content that I want to share that's not really a full episode for the main channel here. I've got a few videos on there already, like video capture from a couple games, a demo, and an audio-only talk about some of my first memories of emulators from back in the 80s and 90s. Link to the channel in the description below. Now, here we go. The first one is pretty puzzling to a lot of us. I know I couldn't make heads or tails of it at the time. It's this define function. If you've programmed in more modern languages, you've surely used some functions, and it's a good way of making your code a lot cleaner. Commodore BASIC doesn't support it very well. There is the subroutines with a GOSUB, but you can't pass a parameter in and get a value back like you would in a function in a C-like language or whatever. Well, it actually does have support for simple functions. They can only be mathematical, essentially. We'll look at them here. So you just give it a variable name, and you can give it the one parameter name. It only supports one parameter, so we're just going to say x. And as a very simple example, we'll just have the function return 5. So the x parameter is unused. And then to call it, you just go print function a and pass a value in. You do have to pass something in, even if it's not going to be used. That's called a dummy argument. And we'll run it. And you see, it returns 5. So, of course, we can make that a bit more complicated. We can take the parameter that's in, multiply it by 2, and then when we run it, the 1 that we're calling it with is multiplied by 2 and returns 2. Okay, so that's not particularly useful, but that's just a really simple example to show how easy it is to define them and use them. Now, for a more practical use, we can define two functions here, one called high, and that will take the parameter and return it divided by 256. And let's make one called low. And that one is going to take the parameter and subtract the integer of x divided by 256 times 256. Because Commodore BASIC doesn't have a mod function, that's essentially what this is, a modulus function, and I'll show you what this does. Let's go input a to ask the user for a number, 40, and then we're going to print function high and pass that parameter in, and low, and go to 30. So what this does is if we just type in any number, like the famous 49152, it prints out the high byte and the low byte. So now we've got a function that will split a 16-bit value into its two-component 8-bit low and high, or high and low bytes. So 192 decimal equals C0 hex. So this is C1000, as I call it, or C000. Another one, 32768, should return 128 and 0. Whoops. I cursored around too much there. Okay, there we go. 128 and 0. Yeah, because I was messing around with the cursor there, that messed up the input function. Okay, and if we do one number bigger than that, 769, it should return 128 and 1. And if we return, or if we do one value smaller than 768, 767, that should return 127 and 255. So high byte and low byte, 0, of course, returns 0 and 0, and the maximum 16-bit value is 65535. That'll return 255 twice. If we try put a value larger than 16-bit in there, then you see it goes up to 256, but this is actually a 9-bit value there. Okay, and to get out of an input, we actually have to hit stop restore. List it. So anyway, that's just an example of how you can define a possibly useful function. Note that this section can't have any if-thens, no loops or anything, so it is very limited in what it can do, but you can do any mathematical operation and call any function. Okay, number 2, the little used on command. So let's again just input the value A, and then here we go, we'll on A GOSUB 100, 200, 300. So this is going to use this numeric value, and if it's number 1, it's going to GOSUB the first parameter, number 2 the second parameter, 3 the third parameter, and so on. If you pass it a 0, it will just ignore the on statement and move on to the next line. If A is negative or greater than 255, then you'll get an illegal quantity error. So we'll just go to 10, and then each of these subroutines, we'll implement them. 1, and return. Of course, these are just, these aren't particularly useful. I'm just giving an example to help with understanding it. Okay, and now we'll run it. So if we input 1, then it has called the subroutine at 100 and prints the word 1, 2, 3. If I put a 4 in, then you see it just ignores it, and 0, it also just falls through from line 20 to 30. And if we put in a negative value, it actually crashes with an illegal quantity error, so it's up to you to do boundary checking there. So if you've programmed in a C-like language, you may have used the switch statement, which is a good substitute, as this is, for a whole bunch of if-thens. If A equals 1, then GOSUB 100. If A equals 2, then GOSUB 200. So this is a much more compact way of making multiple choices based on a numeric value. It can be really handy. It certainly helps in making your program more compact. Okay, the third one, this is actually a statement, but we'll print out, let's input a value and print it out. Now, of course, if you just type a number in, it prints it back. But did you know that you can type in numbers like 55E2? And that E is the scientific notation, so it's actually the equivalent of 5500. The E2 stands for 10 to the power of 2. So if we just do 1E1, that's 10. And if we go 0.01 E2, that should equal 1, because it's 1/100th times 10 to the 2, so it's basically 0.01 times 100, which equals 1. So this is an alternative notation. When your program is expecting a numeric value, you can legally type in this E to type in very large or very small numbers. Actually, this reminds me, last year when I had a real job programming in C#, the QA people noticed that in this web form, you could type in a numeric, that was expecting a numeric value, you could type in an E value just like this. And they were pretty upset that you could type an E into a numeric field. And I tried to explain, well, these are numbers. But they weren't having any of it. Okay, so we used input there, but Did you know that you can ask for multiple values to be input at once? And for our test program, we'll just put those back out. So if you run it and you just give it one value, say 1, then you will get this double question mark prompt to show that it expects more. So we'll give it another 1. It doesn't go up to triple prompt though. 1, 2, 3. There, and now it's printing back the values 1, 2, 3. You see, when in a print statement, commas actually move it to the next tab, which is every 10 characters. But it has some other quirks to it too, like if you type in that, and then we again type in the 2 and the 3, you'll see that it's converted this number 1 space 1. It's gotten rid of all those spaces and turned it into a single number. What it really expects you to do is to do comma separated values like so. Next one, if we just make a short little program here. Okay, so we've got this little 4-line program. So when we type, well, obviously I just type list and it shows the whole program. You can list an individual line number just by typing in the line number. You can also do a range, such as list from 20 through 30. But you might not know that you can do a range like this. That's everything up to and including 20. And if you want to list from 30 on, then you actually type the minus on the other side. So just in case you didn't know that, L-Shift-I, just like most Commodore BASIC commands, you can abbreviate them by typing the first 1 or 2 letters and then the next letter shifted. I did a video on that before. You can also slow down the listing process by holding Control, and you see it displays at 1 line at a time. Okay, the next one is that we have 2 commands here. You're probably familiar with the end command. And just to show that it does end the run of the program. See how high doesn't print. Now a lot of the time we might not use the end command because it automatically happens if the program runs all lines, if BASIC executes past the last line. There's also a stop command, and that's almost identical, except that it prints out the break in 10 message. And I don't know of any other difference except that end just prints ready, so it's useful in a final version of a program where you just want a clean exit. And perhaps if you're debugging or need to tell the user for some reason where the stop occurred, almost like a breakpoint, you can use the stop command and it will print out this message, and then you at least know where the execution was. Another command that you might not know is continue, and that just continues execution on the next command after the stop or the end. So you see now line 20 is executed. Actually, this is pretty weird that you can run a program like this, and obviously the programmer intended it to end here, and the user can just type continue and get the program to keep running even if that code had nothing to do with the original run. Anyway, but here's a weird thing about the continue command. If we make a program like this, line 9999 and end, and we run that, okay, as you expect, it doesn't do anything except just prints ready. But now if we type in new and put continue as a basic statement and run that, the computer will appear to freeze. It is waiting for you to hit the stop key. Basically nothing exits, but if we press stop, we get this break in 9999, okay? But if we list the program, there is no line 9999 anymore. BASIC appears to remember the last line number that was either stopped or ended. And in this new program, because there hasn't been a stop or an end, it's still remembering the old value. Seems kind of like a bug, but just kind of a curiosity. I saw that one on C64 Wiki, which I highly recommend that website. They've got a page for every BASIC command there is, and lots of interesting information on there. I'll put a link in the description below. Okay, another one is the random command. Of course, this gets used quite a bit. Right here, if we print random 1, okay, that tabs over and then holds the place on the line for the next statement, doesn't insert a new line. And then go to 10. Okay, if we run that, we'll get a sequence, 0.185 and so on. Now if we run that again, you see the sequence continues on. There's no repeated numbers here, but every time we power cycle the computer and do the same random 1, we're actually going to get the same sequence. So check out this first value here, 0.185. Okay, I'm going to turn off the C64. I've waited several seconds. And we'll type in that same program and run it. And you see here, same so-called random value, even though the computer was cycled. So if your program is just using random positive parameters, and I shouldn't just say positive, parameters above 0, then you're actually getting the same random sequence every time, and that's probably not what you wanted. So a way to solve that is to simply use random 0, which reads from the time clock. We'll run that. Okay, 0.37. And once again, I'll power cycle. And this time I got 0.57 as the first number back. So the lesson there is to use random 0 instead of random 1 if you want truly random sequence. And actually it's a very small performance increase if you use random dot. That is the same as random 0, but it parses slightly quicker. But there's a whole other aspect to these random numbers. If we add an extra line, print random, and then we do a negative value, and then we change line 10 back to a positive value, or an above 0 value, and we run that, I'll explain that first value in a bit. We see here the sequence is 0.328, 0.978. Let's run that again. You see how it's the same value here. It's the same sequence each time we run the program. Now there's some cases, say you're going to build a procedurally generated world, for example, then you might want the same random sequence over and over again. And that's how you get it, by first seeding with a negative value and then using a positive value. Now, this can be any number here, 1, 2, 3, whatever, and exactly the same sequence will happen. But when you seed it, when you give it a negative value, that's when you seed it, and each negative number is its own sequence. So if we change this to -2 and then run, now our first value here is 0.86 and then 0.84, and we'll run that again, same 0.86 and 84. So there's a whole world for every negative number, and actually even a negative float value like 3.1. Here's 0.33. That's a different sequence. And 0.32. There's another sequence. So actually I got into this in my video about the supposed Microsoft Easter egg wars, which is actually, well, I won't give it away. Check out that video. I'll put a link in the description. I get a bit more into how this whole system works. Now the one thing here is that I'm printing this random seed. That's not the best thing. You always just get kind of a useless value back. I actually don't completely understand. I guess it's just the representation of what you've typed in here. I actually haven't studied that yet. But if you just assign it to a variable like that, then that initial garbage value won't print out. Okay, two more. Now you probably know about the command like the famous 64738, which resets the computer. But there is another command called user, and it's just like this, print user, and you just put a value in. It's a function. You can pass a parameter, like just a single number again, through to your machine language routine, and then it will come back. This is better than sys in the sense that it's easy to send and receive values for it and use it in a function like this without having a peek or poke. But the disadvantage is that you can only have one user routine at a time, and to set it up, you have to do a couple pokes ahead of time. We'll just run this here. You see how you get an illegal quantity. Well, when you first power up the 64, the user function just points at the routine to call this illegal quantity error. So it basically doesn't do anything by default. But it's easy to set up. You just have to poke two values. Poke 785. This is the low byte of the value. You could use that function I showed you earlier to get this if you don't know how to calculate it. So it's the low byte of the address where the machine language user routine will be. And 786 will poke with 192. So this is pointed at C1000 hex 49152. That's 192 times 256 plus the 0 is 49152. And then we'll print out user 1. You do have to pass an argument to it. So our program is set up, but we haven't set the machine language part yet. So I'm going to pop into my Super Snapshot monitor here. And we'll just do a very simple program at C1000, that is 49152, and we will increment the screen color, and then we will return. Okay, that's all there is to this first example. So now when we run it, there, it changes the background color. We'll run it again. That's pretty ugly. Ugh. Wow. Oops. Okay, so that shows you how easy it is to set up a user routine. That's a pretty useless one. Note that that's just a dummy argument because we're not actually using it. We're just incrementing the screen color no matter what. So let's make a slightly more useful one. Back into the monitor again. And again, we'll assemble at C1000. So I've got my mapping the Commodore 64 here. And that user function uses this location 97 through 102 decimal, the floating point accumulator, the exponent, the mantissa, 4 bytes of mantissa, and then the sign. So that's actually 6 bytes in total. And this is both how BASIC stores its floating point numbers in this format, and it makes it available to the machine language program. And then if you want to return a value through the user function, you also store it in here, and that's passed back to your BASIC program. So we're not going to do anything really complicated. We're just going to try incrementing this exponent, and we'll see what it does here. So that's in hex location 61. So we're just going to increment 61, and then we'll return. All right, and we'll try running that program. There, and we passed it 1, and it returned 2. Let's pass it 100, and we'll run that, and it's returned 200. I think we can use that in immediate mode as well. Pass it 5,000, and it returns 10,000. So all we're doing is incrementing the exponent, which is a power of 2, so that's the same as multiplying by 2. So of course you could probably think of a more useful function than just multiplying by 2 here. If you've got a basic program and it needs a big speed up in a certain mathematical function, this is possibly the right way to do it. And finally, the wait command. Now this is one that hardly ever gets used. It's a strange one too. Basically it waits for a certain location to have a certain value. So if we wait for location 1 to have a value of 32, and actually that's inverted again, so that's actually waiting for the tape unit for a key to be pressed. That's finally going to use this. That's why it's being seen here. So I'm going to press the play button. You see how the wait command returned. And we can run that again and even press like the fast forward button here. Stop. Nope, that doesn't work. Eject. No. But it works for these play buttons. Probably record button, but I don't have the blank tape in there right now. Here's another example. Wait 653, 2. And that's going to wait for us to press the Commodore key. There. And one more. Wait for 203, 64. So again, this is, okay, so that one didn't seem to do anything. But watch this. I'm going to press and hold return. See how the cursor isn't appearing this time? It's waiting for me to release the return key. There. So essentially the wait command is rapidly peaking a certain location and waiting for that value to appear in that location. It's faster, much faster than actually doing a peak loop, but the disadvantage is that while it's active, you actually can't hit stop. Like I'll do that Commodore key one again. Look, I'm pressing stop key. You can't break out of it, but you can use stop restore to get out still. Now you notice this first command actually had 3 parameters, while these other ones have 2. So what's happening is this first value is getting ANDed. So it's like peaking location 203, which is reading the keyboard. Let's check that. Yeah, according to mapping the C64 here, this is the matrix coordinate of the current key pressed. And 64 is the no key pressed. So it's waiting for that value. When you add this third parameter, it's actually doing an exclusive OR on the value to flip any bits. And that's useful when you have a bit that is normally 1 and you're waiting for it to turn 0 instead, which is the case with the dataset keys. Now the thing is, because your basic program gets kind of killed while it's waiting, it's like in a busy loop waiting for something to happen. Commodore BASIC isn't multitasking. You can't have another part of your basic program change a memory location. So it's not a very useful command because of this. So really you're dependent on waiting for the kernel, the operating system, to change a value, or the user through the various input-outputs available, such as keyboard, the data set, or if you have a joystick plugged in, you can wait for those kind of values. Anything that will change without BASIC's participation. So one other wait we can do is waiting for 56320, which is where we read the joystick, and waiting for a value of 16. Again, because the button is normally 16 when you're not pressing it, we're adding the third parameter to invert that bit and wait for it to be 0. So if I press the fire button, there, it's ready. If I get rid of that 16, then you see it goes back to the ready prompt right away. But if I'm holding down the fire button, or ready, and press return, now the cursor isn't there until I let go. I found it very hard to understand that wait command when I was a kid, and it's only these kind of examples that have helped me to understand it now. Okay, so I hope you found that interesting or informative, or both. Thank you for watching, and especially thank you to my patrons on Patreon who support this channel. And also, you'll notice the new credit screen here. Those are my patrons' names scrolling up the screen. And that is thanks to my friend the Fatman, who has coded that credit screen just for us here at 8-Bit Show and Tell. So thank you very much, TFM. It's an awesome job. If you'd like to see your name scroll up the screen or any of my other perks I have available, check out my Patreon page. Again, thanks for watching, and we'll talk to you next time.